Hi, this is Dave Johnson with another edition of Math Off Topics. Today we're going to do a limit that can't be done by L'Hopital. And one of my commenters on an earlier video presented this problem to me, and so I'm addressing it here in this video. And thank you to that commenter. So a lot of students, once they find out about L'Hopital, they fall in love with it and they want to use it all the time. But there are a lot of limits that can't be done easily or at all using the L'Hopital rule. So here's an example of that. Let's get into it. So limit as x goes to infinity of e to the x squared divided by x e to the x. If you substitute in infinity for x, you get infinity over infinity. So this is a indeterminate form that L'Hopital can supposedly do. I'm not going to work out the details of this, but if you take the derivative upstairs and downstairs, you're still going to have an e to the x squared upstairs. You're going to still have an e to the x downstairs. And so you're still going to have an infinity divided by infinity. So, and successive differentiations isn't going to help. There is no way to algebraically simplify the e to the x squared divided by e to the x. There's no way to reduce that to turn it into something else that I know of. If, by the way, if you do know of a way to do this, please leave a comment below and I would be very grateful. So, the standard way of doing a problem like this would be to set the whole thing equal to L. There are other ways to do this, but we'll just set this limit equal to L, assume that a limit exists, and then take the natural logarithm of both sides. So ln of the limit as x approaches infinity of e to the x squared divided by x e to the x is equal to ln of L. Now, by the way, this problem is just as hard without the x in the denominator right here. But to spice things up, I think somebody decided to put an x there. It doesn't really change the nature of the problem. So now, one thing that's a little subtle about limit theorems in general is that you can move this ln inside the limit, and you can do that as long as the function, so in this case, ln of this is continuous as x goes to infinity. And that is the case. It might be different if x were going to 0 or some other value if the expression were different. But in this case, I can move the ln inside the limit. So let's do that. So we get limit as x goes to infinity of ln of e to the x squared divided by x e to the x. And now this is all going to be equal to the natural logarithm of L, but let's go ahead and expand this. So limit as x goes to infinity, I'm going to use a log property here. So let's put this in brackets. So we get ln of e to the x squared minus ln of x e to the x. And continuing to expand, so limit as x goes to infinity. Um, so the ln of e to the x squared just becomes x squared. And then ln of x, so minus ln x and minus ln of e to the x, which is just going to be x. Okay. Now we have a limit problem that we think we can do, right? One way to do this, now you got to be careful because this becomes infinity, this is infinity, this is infinity. So infinity minus infinity is not 0. Uh, so we end up using, well, let me go ahead and write it and you'll see what's going to happen here. So the limit as x goes to infinity, I'm going to factor out the x squared and I get 1 minus and then ln x over x squared minus and then x divided by x squared, which is 1 over x. Now, you might say, well, wait a minute, L'Hopital does come into play here, but not in the way most people would think. So obviously, as x goes to infinity, becomes infinity, but and this becomes 0, but this also becomes 0. And I'm not going to separate this out and do this as a separate problem, but if you apply L'Hopital to this, you will get that the limit of this is 0. And the way to see that really is that the natural log of x grows much, much slower than x squared does as x goes to infinity. So the numerator is small compared to the denominator, and that difference just gets bigger and bigger as x gets bigger. So what you end up with is an infinity times 1, which is effectively infinity times 1 is infinity. So on the right-hand side here, you're going to get infinity. And so, but that was equal to ln L, so the natural logarithm of our hypothesized limit L is equal to infinity. If we exponentiate both sides base e, we get L is equal to e to the infinity, which of course is infinity. So our limit, our final answer, is infinity. I hope this has been helpful. If you have any questions or comments, leave them below. I'd love to read your comments. And like and subscribe, and I will see you in the next video.